In the last video, we have seen that if f is a homogeneous polynomial, then it has a well-defined vanishing locus inside Pn. But then for the affine varieties, we didn't just look at the vanishing loci of individual functions, but it was actually much nicer to look at vanishing loci of ideals. So we can ask the question, what ideals of this ring have well-defined vanishing loci? And the answer is it will be homogeneous ideals in the following sense. By saying an ideal in a graded ring is called homogeneous if it can be generated by homogeneous elements. And here note, these don't have to be of the same degree. So as an example, inside this ring here, in three variables, we have I1, a homogeneous ideal with these generators. You see one generator homogeneous of degree 1, one generator homogeneous of degree 2. We have different degrees, it's still a homogeneous ideal. The second one, I2, is not homogeneous. I2 is generated by x0 minus x1 squared. So certainly this generator of the ideal is not homogeneous. And then it's a short exercise to show that this, in fact, does not have any homogeneous generator. And for that, you basically assume it had a set of homogeneous generators. Then you can get a contradiction using nice properties of this ring. It's not a totally trivial exercise, but still, it is true this is not homogeneous. And so note that not every set of generators has to be homogeneous. So it doesn't just suffice that this set here that we wrote down is non-homogeneous, because this nice homogeneous ideal, you can write down a non-homogeneous set of generators just by replacing the second generator by the sum of the two generators. Clearly, this doesn't change the ideal, because you can just subtract this again if you like, but this will no longer be a homogeneous element. So keep that in mind. It's just necessary that you find some generating set of homogeneous elements. And then this here is the big master lemma about homogeneous ideals. So if you have J, J1, J2, any ideals in a graded ring, then first of all, we give a criterion for being homogeneous. J is homogeneous if and only if any element of J satisfies that if you decompose it according to its homogeneous decomposition, then all the homogeneous summons are also in the ideal. So F in J implies Fd in J for all D. The second is that all the standard constructions that we have with ideals send homogeneous ideals to homogeneous ideals. So if you have the sum or the product or the intersection of two of them, then they will still be homogeneous. And if you take the radical of a homogeneous ideal, it's also homogeneous. And then the last one is that that's similar to the statement that if you have a ring modulo an ideal, then you get a ring. It's true that if you have a graded ring and a homogeneous ideal, then R modulo J is again a graded ring, and it has a homogeneous decomposition. Given by this, you have the direct summons are the RD modulo intersection of RD with J. Okay. And as an example for this first criterion here, if you have J, this homogeneous ideal generated by x squared, then you can create an element of J like this. You can multiply this by some polynomial here. And then A tells you both homogeneous summons, so F2 here and F3 of this element are also contained in J, because these things are also still divisible by x squared. And basically looking at this example already gives you a hint of how we're going to prove this part A. So let's see the proof of this lemma. We want to show that an ideal is homogeneous if and only if for all elements of the ideal, all homogeneous summons are in the ideal. And the crucial observation to prove this is the following here in red, that if you have two elements of this graded ring, then the degree d piece of their product can be written as the sum over d1 plus d2 equals d of f d1 times g d2. Well, certainly by the rules of the graded ring, this here sits inside the degree d part because of the summation. And then you can just see that all the other parts of this product, if you expand f and g into its homogeneous summands, all the other parts will have different degrees. And so they don't contribute to the degree d part. Okay, so with this observation in mind, let's assume we have a homogeneous ideal, J, has some generators Hi. And then let's take any element f inside this ideal. Then by definition, it can be written as a sum of gi times hi, where the gi, they don't have to be homogeneous, but at least we know there's only finitely many which are non-zero. That's a general element of J. And then what we want to show is degree d part is still in J. But by this equation here, the degree d part of this is the degree d part of all these products. And so we just get the sum. And then the only way, if hi is homogeneous of some degree, the only way that this product here can be homogeneous of degree d is that that you take the d minus the degree of hi part of g. So, I mean, it's a short observation, that fd can then be written as such a sum. And then we see this is an element of J, because again, it's a linear combination of elements of this generating set by some elements of the ring. Okay, so this was one part. And then the other part is assume you have an ideal which satisfies this criterion. F in J implies Fd in J for all D. Then our claim is J is a homogeneous ideal, and in fact, it is generated by all of these Fd, where F is in J and D is in N. And so we want an equality of ideals, and so we show the two inclusions. One of the inclusion is very easy because it's exactly this condition here. It says if F is in J and D is in N, then Fd is in J. So all the generators of this ideal are in J, so the ideal is also in J. So this was easy. And the other is also kind of easy, because if F is in J, we want to show F is in this ideal, but F is just the sum of its Fds. These are clearly in the right-hand side ideals, so F is also in the right-hand side. So, I mean, not a lot has happened in this proof here, but in fact, we're going to see that this condition A is really very useful. We're going to use it basically in all of the rest of the proof. So the second part, B, is that homogeneous ideals are closed under all the natural operations. So let's say we have two such homogeneous ideals with some generators Hi and Gj. Then their sum has as generating set just the union of the generating sets. And this is, all of these are still homogeneous, so this is a homogeneous ideal. Similarly, the product of the two ideals has as generating set, well, the set of products. These are still homogeneous. The product of two homogeneous things is homogeneous. And so these were very quick. For the intersection, we actually use the criterion from A. So if F is in the intersection, well, by definition, it's in one and it's in the other ideal. And then by A, all of its FDs are in one and the other. And then by definition, that's the same thing as saying FD is in the intersection. But so if you look at what we have done, we have seen F is in the intersection implies FD is in the intersection for all D. And that, by the criterion on A, exactly tells us that the intersection is homogeneous. So we see it's a very useful criterion. And we're going to apply it again for the radical. And the argument here is slightly more involved, but not super terrible. So somehow assume we have something in the radical. So F is an element of the radical, and we decompose it into these homogeneous factors. Then, by definition of being in a radical, there exists some number such that the nth power of J is in J1. But then if you look at the nth power of this summation here, the top degree part of this nth power is the top element here to the power n. This fd to the n. This is the homogeneous part of degree d times n. All the other factors, or all the other summands in this powers, will have one of them have lower degrees, so somehow all of the rest of the terms are lower degree. So this shows that this is in fact the homogeneous part of degree d times n. And so by A, since J1 is homogeneous, the fact that this here is in J1 means this part here must also be in J1. We have fd to the power n is in J1. And by definition of a radical ideal, this just means that fd is in radical ideal. And then now we reduce the complexity where we observe f was in the radical ideal and its top degree part is in the radical ideal. So if we subtract them, then we get a polynomial of strictly lower degree, which is in J1. And then what we just do is we repeat the argument for this f tilde, and then it will show this now highest degree part is in here. Then we can subtract it, and then one by one, we get rid of all the factors until we just see that f0 is also in this radical. So we repeat the argument, or if you want to have it formally, we do an induction on the degree d of the element f. So we show that all of the parts of fi are in the radical ideal, and then we use the criterion of A in the opposite direction, and this shows that this is the homogeneous ideal. So again, part A was very useful. And then the final part is we want to show that R modulo J, when J is homogeneous, is a graded ring. And its decomposition is this RD modulo RD intersected chain. We're going to just very carefully check all the parts of the definition of being a graded ring. First of all, we want that these things here are subgroups of R modulo J. And indeed, but you can write down a group morphism from RD to R modulo J, which sends F to the equivalence class of F. That's clearly a group morphism with respect to the addition. And the kernel of this, well, something maps to 0 here if and only if it's in J, but then the kernel is just RD intersected J. And by the isomorphism theorem, this means that the image of this group morphism, which is clearly a subgroup of R modulo G, is isomorphic to the domain RD modulo its kernel. So this shows that this thing here is naturally contained in R modulo J. So at least these are all subgroups of R modulo J. And then we want to have the existence and uniqueness of the homogeneous decomposition. We do this in separate steps. So if you have an element f bar inside R modulo J, then, well, it has some decomposition in R. And then the f bar has the same decomposition. Now just put equivalence classes everywhere. And these things are in RD modulo RD intersected J. So the existence part was not so hard. The uniqueness part is also not super terrible. So assume that we had two different decompositions like this in R modulo J. Then we want to show the individual terms are already the same. And then what you just do is you take the difference of some representatives like this. So you just sum over all these degree fd minus gd. And by definition, well, this difference, its class inside R modulo J is 0. This is told to you by this equality here. And so by definition, this means this difference is in J. And then part A comes again and tells us the degree D part of this difference is in J. But the degree D part kind of kills all the terms where you don't put the D in the index. The degree D part is just fd minus gd. And so this is in J, but clearly it's also homogeneous of degree D, so it's also in RD. And so we are in this class, and then taking the equivalence class, we see that this is equal to this inside this quotient, and this is exactly what we wanted to show. And so this was the existence and uniqueness of the homogeneous decomposition. And then the fact that the homogeneous decomposition is multiplicative just follows immediately from the same result for R. And so we have put the structure of a graded ring on this quotient here.